Good morning, everybody. Yesterday, we had a lengthy discussion on dipoles and polarity and intermolecular forces. So, as an intro activity this morning, I'd like you to form groups of 2 to 3 and discuss your molecules that you've chosen for the analysis assignment. And I want you to identify what types of polar bonds you notice in the molecule, whether you think that molecule overall is polar or nonpolar, and then based on that, discuss with one another what types of intermolecular forces your compound can go through. I don't want to spend too much time on this, so get your molecule pulled up, or if you remember what it looked like, you can just describe what bond types are in there. And let's spend about 5 minutes discussing with one another your molecules' IMFs, okay? I'm happy to break you into groups if you want to, but I know at this point you guys have gotten to know each other pretty well that I think you guys can organically, no pun intended, break up into your own groups. It's a curse. Everything's fallen.
Brett, you can slide over. You're welcome to slide here, there, wherever you want to go. What molecule did you choose? Capsaicin? So pepper. Is it pepper, is it cream, or is it both? Like that?
Cream?
Yeah, because if you get cream out of like capsaicin, like that pepper.
God, could you imagine like applying it to your skin or what?
People do. It helps with pain.
Oh my gosh. By distracting, by creating more
I don't know
pain?
if it's like pure. Yeah.
Ah. Yeah, it's organically synthesized in peppers.
Interesting. Okay. Yeah. I guess you haven't reached that age yet, but arthritic pain, man. Cool. Pull it up and see that.
That's a little hypothetical.
I think neurotransmitters are interesting just in general, just how they work and how they seem to function with so many different aspects of how you experience things. So I just found dopamine really interesting in sort of the scenes. Again, it's just surprising how all of these things are built from very similar parts.
Yeah, and hydrogen bond.
Like there is a little bit of complexity to it. I mean, it's just hydrogen, oxygen, and nitrogen. Maybe. Yeah, that's just all.
Carbon and hydrogen.
Radius.
It's got some polarity in there with heavy polar.
And it's
I mean, that's just, I look at the guy was
Yeah, I was looking at some other ones when I was like researching. That's not what it was to do. It's not hardly why.
yeah, just the structures.
Well, like,
and so I just basically looked at what satisfied this criteria, but also going off of like this.
I mean, I guess the hydroxyl
It also
could
yeah, like, you know what I mean? They're all attracted, really carbon, it's all attracted to chlorine, so they're going but now you guys touch each other. Yeah, like they're attracted to the oxygen. And like water would be interesting, no, it's just trying to
Oh my god.
I guess you can. Wait, I should get Jeff.
But mainly because the only flares gonna be there. And it's in there too. So I think it's gonna be like your water. It's gonna be the that's the polar to the outside.
Okay, so Jeff. Jeff, we're gonna look at it. Does it have a well, that's what I
Yeah, because the way it's for long term, we're gonna oxygen pushing it out that way.
yeah,
Yeah.
Okay. Sorry, I actually just went through and finished grading the rest of your submissions for that assignment. So for anybody that wasn't sure if you were going to be able to use yours, I think I had to turn down one person. And I told them I can make it work, but it's going to be a little challenging. What did you guys find in your discussions? Did a lot of your compounds have an overlap in their intermolecular force capacities? Or did some of you have a compound that was really limited, and then others compounds that just had every type? What do you think? Am I being too vague here with my question?
All of our molecules have lots of polar bonds, have hydrogen bonding, and dipole attraction.
So everybody's molecule had dispersion forces, because that's present in every molecule. And it's really challenging, especially since I required that your compound has at least one heteroatom. It's really challenging for any of you to have a compound that doesn't have a permanent dipole, and to find a compound that doesn't have dipole-dipole forces. So I totally expected you each would find dipole-dipole in your molecules. But how many of you did not have hydrogen bonding capacity in your molecule? Right? So a lot of organic molecules have an NH or OH bond. Or also lone pairs on an oxygen or a nitrogen. So sometimes within a pure sample of your compound, there will be a lot of hydrogen bonding. But even your compound dissolved in water could do a lot of hydrogen bonding. Most of you probably found that your molecules were fairly polar as well. But because I also put a restriction on how many carbons you had, meaning that you had to have at least 6 carbons in your structure, a lot of your compounds would be soluble in organic solvents, just because they've got a lot of dispersion forces from having a lot of surface area, and a lot of that interacts well with organic solvents. Whereas some of yours, having so many carbons, even with the capacity for hydrogen bonding, can decrease its solubility in water. For instance, Jamie picked benzocaine, which is an organic compound used as a local anesthetic. It's a compound that we synthesize in our OChem 2 laboratory, actually. And benzocaine doesn't dissolve well in water. It's surprising, right? Because it's got a lot of hydrogen bonding capacity on these oxygens, and hydrogen capacity to and from the amine group. The reason that it doesn't dissolve well in water is because it's got this big non-polar region in the middle too. So to make compounds like lidocaine more soluble in water so that they can be ingested easier or even applied as ointments, a lot of organic compounds are then turned into ions. So benzocaine could be turned into a protonated nitrogen group balanced by a chloride ion. If any of you look at your medications and you see blah, 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 organic stuff, chloride, then that means that your organic compound has been protonated into an ion balanced by chloride, making it more water soluble. Kind of cool stuff. That idea of making it ionic introduces an intermolecular force that we didn't talk about last class, a couple actually, which are the ion dipole force. The ion dipole force is what's responsible for water hydrogen bonding to this ion. And of course, it introduces the ion-ion force. I think that you could debate whether ion-ion is actually an intermolecular force or whether it's an intramolecular force. The reason I say that is ion-ion interactions are ion-ion bonds. They're just ionic bonds. And that's what makes up a compound. But we had a discussion last week about compounds being distinct from molecules. So it's kind of a gray area, mostly because of what we have decided the words should mean. All right. Any questions from our previous material before we keep moving on, wrapping up section 2?
Is ion, that's the chlorine, is that just disassociation, or how do you get the compound?
Yeah, an ion-ion interaction is basically the ionic bond. So here, the interaction between the positively charged nitrogen and the negatively charged chloride would be an ion-ion interaction. And we know that those interactions are very strong. Ionic compounds have incredibly high melting points. It takes a lot of energy to break that interaction. but they're not maybe as strong as a ton of ion-dipole interaction, which we can think of as solvation. You take sodium chloride, which has strong attraction between sodium chloride ions, and you put it in water, and it quickly dissociates. You've easily overcome the ion-ion interaction, but it's because you've replaced it with a ton of dipole ion interactions. You've solvated the ions by interacting it with the solvent. Yeah. Okay. We're going to start talking about acids and bases today. I don't know if that sentence is right. I feel like it should probably say, what's an acid? What are acids and bases? What's an acid and base? Sorry. I'm not an English professor, okay? Chemistry is a language of its own. What did you say? Actually, in my notes, I just have what's an acid / base. So I feel like that's even better English than what I have up here. So we talked about the 3 major categories. Actually, I'm going to demonstrate this for you as a Venn diagram. It's a weird Venn diagram because everything fits inside of the big one. At the most narrowest definition, we have the Arrhenius definition. I forget how to spell that guy's name. I don't think that's right. I'm sorry. I'll Google it for you. Arrhenius decided that the best definition... Oh, man, I was so close. Swapped my E and my H. He decided that the best definition for an acid and base was something which, when dissolved in water, produces acid, produces H3O plus in water, and a base, I'm sorry, I put an equal sign, but I'm going to say an arrow. An acid produces H3O plus, and a base produces HO minus. You might be familiar with this idea of acid and base. Hydroxide kind of becomes one of the most common bases. It almost is representative of bases. Hydronium ion, H3O plus, kind of representative of acid. But his definition is very narrow. And Brønsted and Lowry expanded this definition. Brønsted said, or Brønsted and Lowry, I don't know these guys. Their definition said an acid produces a hydrogen ion, or we can say an acid is a hydrogen ion donor. And in a way that agrees with Arrhenius' definition, but Arrhenius says water has to accept the hydrogen ion and become hydronium. And Brønsted-Lowry say anything can accept the hydrogen ion, but an acid is something that donates the hydrogen ion. By the way, if an acid donates a hydrogen ion, that means that it had a covalent bond to the hydrogen to begin with, and that's going to segue us into the next branch here. But their definition of base then is just the opposite. A base is a hydrogen ion acceptor, so something that is not bonded to a hydrogen, but then becomes bonded to a hydrogen. And Lewis's definition pulls back even further. This is the same Lewis, by the way, who's the namesake for Lewis dot structures. Lewis did some important things for chemistry. Lewis says that an acid is not something that just creates hydronium and water. It's not something that just donates a hydrogen, whether it be to water or whether it be to anything else. An acid is something which takes an electron pair. Because the acid in each of these other smaller definitions is originally bonded to a hydrogen and then takes that bond back for itself. So an acid is an electron pair acceptor. If you are a hydrogen donor, then you must be an electron pair acceptor. That's how you got rid of the hydrogen. And a base, quite the opposite, is an electron pair donor. So all Brønsted-Lowry acid bases are Lewis acid bases because there's always an exchange of electrons. Electrons are moving when hydrogen ions are being donated and accepted, but that's not necessarily true in reverse. Not all Lewis acids have to involve a hydrogen ion. So let's give an example of our Lewis acid base because there is a lot of important chemistry that revolves around donating, Brønsted-Lowry acid base. There's a lot of important chemistry that revolves around donating and accepting ions. We can do a couple of things to represent acids and bases. We can write them as generic equations. An acid can be represented as HA, H being the hydrogen, A being the acid, and in a chemical equation, H plus is donated and A minus is formed. What is the name given to A minus in respect to HA? It's not the conjugate acid, it's our conjugate base. There's that word conjugate again. We talked about conjugation earlier this week in regards to p orbitals involved in resonance. And we said that an uninterrupted series, a connected series of p orbitals are said to be conjugated. They're related to each other. And the idea applies here. That base is related to that acid. It is the base produced by that acid. And conversely, HA is A minus's conjugate acid. So they have a forward-backward relationship like that. We can represent a base in a couple of ways. Bases are sometimes neutral and then take on a positive charge. Bases are sometimes negative and then become neutral. Let's say that this base is neutral and it reacts with a hydrogen ion to form BH plus. Again, BH, the conjugate acid, could be neutral if the base was negatively charged. So there's a lot of variance here. And then we can sum these equations together to give us a balanced chemical equation. The reaction that occurs between HA and B results in BH and A minus, BH plus and A minus. Where did my H plus ions go? One more time, your They what? Not quite. I do like that. Kaisa? Sorry? They turn into water, but then I think that we need to show them maybe as like H3O plus. Right. What we could say is that they cancel out. This H plus that forms is taken as this H plus by B. So I'm summing these two equations. On the left-hand side of my arrow, I have HA, B, and H. And on the right-hand side of my arrow, I have H, A minus, and BH plus. So I have H plus on the right, H plus on the left. That's like a mathematical equation having 3 on the right and 3 on the left. They can just cancel out. So H plus cancels. And I'm left with the net reaction. An acid reacts with a base to form a conjugate acid and a conjugate base. And then there's this concept that you guys learned in OChem or Gen Chem 2, talking about the acid dissociation constant. To what extent does a molecule of acid break apart into its conjugates? And we can actually apply it to this chemical equation as well. The problem is the acid dissociation constant is such a big number, or a small number, but it has a large exponent when multiplied by times 10 to the large exponent. So we take the pKa. P there is just a mathematical function that says show opposite the log of the number. And so that is opposite the log of the concentration of the products over the concentration of the reactants. So for an acid, that is H plus times A minus over HA. And we could also write the pKa for the conjugate acid of a base as well. If we were talking about the pKa of the base, then we would say it's opposite the log of, we're looking at an acid dissociation constant. So we'd want to look at the concentration of H plus times B over the concentration of BH plus, which is to say, how well does BH exist and how much does BH split apart? It's actually looking at BH in reverse. So in an acid-base equation, I can identify 2 acids. One acid in the starting material, one acid in the product. I can identify 2 pKa's. The acid dissociation constant in the forward reaction and the acid dissociation constant in the reverse reaction. So I'm going to make a change to the reaction that I've shown here without having to erase anything. Got your eyes on the board? What have I just informed you by making that one additional arrow? This reaction occurs in equilibrium. It does not have to go one way or the other. It can go both ways. I can build a sandwich, and I can take that sandwich apart into its constituents. I mean, unless I eat that sandwich first. On our homepage, we have this link to functional groups and pKa tables. You'll have to scroll down past the functional groups. And then I've got this table. In the middle are the pKa values for the acids that are shown on the left. And then the conjugate bases are shown on the right. And you'll notice I use some different arrows in here. Sulfuric acid is not shown with an equilibrium arrow between its acid and conjugate base forms. That's because sulfuric acid, I don't know why I called it hydrogen iodide. That's pretty weird. I should have called it hydrochloric or hydroiodic acid. These acids are such strong acids, they essentially never exist. If there is anything else that has any capacity to take a hydrogen, it will give away its hydrogen and it will exist as the conjugate base. Then you can see these strong acids where the equilibrium arrow is actually larger to the right-hand side. When we draw an equilibrium arrow that is larger to the right, that means that we're saying the reaction favors the products. Or in other words, there's a larger amount of product at any given time than there is starting material. The application here is there's a larger amount of conjugate base at any given time than there is the actual acid itself. These ones, we basically say they don't exist as the acidic form. They immediately give away their hydrogen. Here, they largely exist as the conjugate base, but there's some presence of the acid. And then we get to a couple of equilibriums where it's close to a pKa of 0. That means nearly a balance between the conjugate acid and conjugate base form. And then we've got the reverse arrow of what we had up here, which is to say this favors the reactants. At any given time, the acid makes up a large amount of equilibrium, and the conjugate base only exists to a small extent. It's not very good at donating its hydrogen. And we can actually describe these acids in that way. We can say that a strong acid is good at its job. A strong acid donates its hydrogen all the time. And a weak acid is not good at donating the hydrogen. It doesn't prefer to donate its hydrogen. As you come down on this table, you'll notice that the arrows eventually flip. So here's a conjugate acid and a conjugate base of a carbon atom. And this is trying to tell us that the conjugate acid always exists. This hydrogen this carbon never gives away its hydrogen willingly. But if you can find an example of a carbon that has a lone pair, anything that it can rip a hydrogen away from, it will. It does not exist to any large extent as its conjugate base. So what we can start to do then is predict favorability between equilibrium. And we can do this using pKa values. So I want to take a couple of examples, ones that might seem counterintuitive to us. This is methanol, a very common organic solvent. And if I take methanol and I react it with sulfuric acid, then I can make the protonated form of methanol and the deprotonated form of sulfuric acid. There's a preferred equilibrium in one direction. Well, sorry, let me put my equilibrium arrows because we're not sure which way is preferred. What we can do to help us make sense of this equilibrium is look at the pKa values. I'm going to find one pKa value for the right-hand side and the left-hand side of this chemical equation. Because there's one compound that's acting as an acid in the forward, and there's one compound that would have to act as the acid in the reverse reaction. Is methanol or sulfuric acid the hydrogen ion donor in the starting material? And we know based on the base, sulfuric acid is the hydrogen donor because it loses a hydrogen. So let's look at the pKa value for sulfuric acid. We find that its pKa is about -10. That's to say that the acid, or the distribution of ions here is about 10 to the 10 times larger on top than it is on bottom. 10 to the 10 times is like 10 billion times more of these compounds exist in solution than this. And what about this? My protonated methanol. What is its pKa value? Well, if I look at this table, you'll notice methanol never shows up on here. But there is a compound similar to methanol. It just has one more carbon chain. And that compound similar to methanol, well, that's being shown as an acid itself. That's not what I'm looking for. So this would be a predictable range for me if methanol was the acid. But instead, I need protonated methanol. So I'm going to move up here where I find the hydronium ion. Now, hydronium ion is not protonated methanol, but if I took out one of those hydrogens and bonded the oxygen instead to a methyl, that's essentially the methyl protonated, or the methanol protonated compound. So water is basically an inorganic alcohol, and the pKa of protonated water is very similar to the pKa of a protonated alcohol. So the pKa here is about -2. So one of these acids is as strong as having a pKa of -10. One of these acids is as strong as having a pKa of -2. Which of those is a stronger acid? -10 is a stronger acid. The lower the pKa value, the more negative the pKa value, the stronger the acid. So which of these acids does its job better? Which of these acids exists to a smaller extent at equilibrium? Sulfuric acid does its job better, and by the time it's done doing its job, it doesn't exist. So this is stronger acid, and this side of the equilibrium is favored. That is to say, when you mix neutral sulfuric acid with neutral methanol, you can expect to get a high concentration of protonated methanol and deprotonated sulfuric acid. And if that feels weird, that the reaction favors becoming ionic, it's okay. It's all about which species is able to push off its hydrogens better. Let's do another comparison. Let's take methanol in the presence of the acetylide ion.
Is it? I was told once that when you're determining like if the products or reactions are favored, if the pKa value is bigger on one side.
Well, what does bigger mean?
I don't know. That I was just curious if that's like a correct way to think about it, or if that's not.
I would say this is bigger.
Well,
So what I like to use is more negative or more positive.
I guess more positive is what I meant.
Okay, so can you say it again? If one side is more positive than it is,
Then it is like favored.
yeah,
Okay.
that's a good way to look at it. It's not necessarily understanding it.
Yeah.
And I want you guys to be able to rationalize. This is a stronger acid. It does its job better. When it's done doing its job well, this is what exists. So this side exists at equilibrium. But then the trend that you can always lean back on is the more positive the pKa is the favored side at equilibrium. Absolutely. And that's because it's a weaker acid over there. It's not as good at doing its job.
Can you say what you said again, that protonated water acts as
Protonated water is comparable to protonated alcohols. And also the pKa of alcohols is comparable to the pKa of water. So water is basically inorganic alcohol. It shares a lot of the similar properties. I want to do Russ and then we'll do Brett.
Just protonated means that it's accepted a proton, it's accepted a hydrogen.
That's right.
Okay.
Yep. Protonated, taken the proton. Deprotonated, given its proton. And proton, obviously protons are very fundamental to the core of a nucleus, but that is the nucleus of the hydrogen ion. Feels a little bit like a scam to me, if you're honest. That the proton is a hydrogen nucleus. It's fine though.
I'm a missed part, but did you just get like the pKa -10 and -2 just from the chart?
I grabbed it from this chart.
Okay.
Yep. And so those might be approximations, especially the -2, since it's not an exact math. I'm not asking you guys to memorize pKa values. And I'm also not giving you this chart on exams. That's because we're going to figure out a way to rationalize pKa's or rationalize acid-base reactions. On your unit test, you will have something like this where you're given pKa values, and then you can use those pKa's to rationalize what side of the reaction is favored. But more often than not, we're actually just going to take a series of compounds and try to rank them. And we're working our way to that. Let's see if we can predict the products that form here. You might be able to say, well, both of the compounds here have acidic hydrogens, so how can I know which one is going to do what? I'll give it to you. The products that we'd expect here are CH3O- and HCCH. So we want to understand now, will I run into any issues if I introduce this carbanion with this OH group? Will they just exchange the proton in this way? We'll need to identify pKa values. What's the acid on the left-hand side of the equation, the forward reaction? What's the acid? CH3OH. And the acid here, C2H2, yeah. HCCH. So, CH3OH, not its protonated form, but instead its normal form. This has a pKa around 15. And if I scroll down, I can find a similar bonding motif here. A triple bonded carbon hydrogen has a pKa around 25. Just so you guys are recognizing that is not negative 15 and negative 25. I'm doing an approximate. I want you guys to think about this for a second. Think about which side is favored by equilibrium. Try to rationalize it. Now just look around with your neighbors. Products favored or are the reactants favored? See if you guys agree.
Because it's like it's more positive. Yeah. So like
But I'm going against that.
at first I was like, oh, like it's the lower numbers. It's like a relative difference. It's the same acid.
We're saying that it's 15 is more positive.
Yeah, so
It's more than
what you can do
more
is
than
actually
five.
take the difference
It was like
in the pKa values
It's just
and
like
you get
it's
an order of
stable.
magnitude of different characteristics.
Yes, okay, cool.
The triple yeah. So this is 10 to the 10 times more acidic in one direction than the other. 10 billion times more acidic. Over there, it's 10 to the 8 times. So like 100 million times more acidic. Almost like billion times more.
If we're looking at
So that makes that
100
times more favorable.
I think we said reactions
Oh,
originally,
I
but
meant
Yeah.
Yeah,
it's
you're right.
25.
All right, what'd you find? Did you all agree on which side was favored?
Yes.
You did. Did you use Carly's trick?
I'm so sorry.
That's
I
okay.
feel really bad.
You
because
shouldn't.
I don't I don't want to be like the easy way out.
It's not about the easy way out. It's about being able to compromise, understanding it with finding the trend.
But I mean, it does make sense. Like if you think about it, like the smaller the pK value or more negative, like it's used up quicker than the excess is left over.
There you go.
I don't know.
But couldn't you say that the reason the trick works is because of the inverse relationship?
Exactly.
So it's really just, you're saying it in a different way.
Yes.
That's why it's not really a shortcut, it's just a different way of thinking about it.
The higher the pKa value, the worse the acid. Of course it's going to be the one that forms. It can't give away its proton. So did you use Carly's trick to say I found the higher pKa value and that was the favored side? Or did you try to rationalize it? Here's something that is more negative. Its pKa value is more negative. So it is stronger as an acid than this. It does its job better. This reaction favors the products. And Jamie asked an interesting question, which was, how much more favored is it? And this isn't a learning objective for us, but you could just take the difference in pKa values.
Could you reframe it a different way, but be the reactants? Because I just thought of leach at liase, and I was thinking since it's a stronger acid, it associates a lot faster. There's less of the association.
And there's an idea of dissociation here, but there's less of an idea of dissociation here. This is a reaction between HA and B without requiring dissociation of the hydrogen ion. So I wouldn't encourage you to think of it with Le Chatelier's principle. This dissociates faster, which means that this forms more, because it's actually, there is no dissociation. It's a direct exchange of the hydrogen ion through electrons.
Do like the triple bonds have any effect on it since it's more stable?
Not necessarily. Now the triple bonds do have an effect compared to other carbon atoms, and we'll talk about that. But they don't have an effect here. Yep. So weaker acid, as this gets formed, it cannot share its electrons quite as effectively, so the reaction doesn't go in reverse. I didn't mean to set up both examples where the forward reaction is favored, because I think that in America we have this, or English-speaking countries, we have this preference to read from left to right, and so we think whatever's on the right is what is favored. We could just as easily have flipped this around, and then we would have said the reverse reaction is what is favored. All right. I do want to talk to you guys about electron arrow pushing, because this idea of did it dissociate and then associate is not quite what happens. So we're going to use electron arrow pushing to explain bond breakings and bond formations. You guys agree that there are no ionic compounds here that are bonded to H+. It's not that I have CH3O- and H+ when I have this compound. There is a covalent bond between those two atoms. I'm going to highlight that covalent bond. And then I'm going to draw my base. A really common, intuitive way to solve this problem is for a first semester organic student to say, well, carbon starts with a lone pair, and then oxygen ends with a lone pair. So I will see students that say this lone pair needs to go to this oxygen. And in the product, carbon will be bonded to the hydrogen. So hydrogen will take this electron pair, the bonding pair, and come with it. An atom can use or lose its electrons in a bond, but it can't give it away to a different atom entirely. And let me say that a little bit differently. Lone pairs can be used by an atom, but lone pairs cannot be lost by an atom. Lone pairs can go to form a bond. They can be used to form a bond. And a bond can be lost, an atom might just straight up lose those electrons. And that usually means that bonds are taken by the more electronegative atom. So I know that my bond, I'm going to draw my products while we're up here so that we can compare kind of what's going on. I'm going to draw in my lone pairs as well. I'm going to draw in those lone pairs on oxygen. What I notice changing in this reaction is that an OH bond breaks and a CH bond forms. Who owns the electrons of the OH bond? The more negative atom, the oxygen atom. So oxygen takes these electrons back. I'm going to show that as an arrow starting from the bond, starting from the electron source, and pointing to the oxygen. It's kind of an ugly arrow, if I'm being honest, so I'm going to try to redraw it. That's how oxygen gets its third lone pair. It took its bonding electrons back. And then carbon can use its lone pair to form a bond. So carbon takes its lone pair and donates them to the hydrogen. So electrons move from high density to low. We've already said that with resonance too. We said that electrons move from high density to low density. When bonds break, they go to the more electronegative atom, and when bonds form, they go from more negative to more positive. Now we don't always use electron arrow pushing on simple Brønsted-Lowry acid bases. We apply them a lot to our Lewis acid bases. So we're going to come back to this idea of arrow pushing. But before we come back to Lewis acids, I want to talk to you guys about how we can make predictions about relative acidity in our Brønsted-Lowry acids. CARIO is an acronym that we can use to try and predict what acid would be stronger. It's not a great way of predicting a pKa, but I also don't care for you guys to predict a pKa, just to be able to predict relative acidities. C stands for charge. Charge can help you predict acidity. A more positive charge often means more acidic. A more negative charge means more basic. We have to be careful about when we apply this because we know it's not always true. Here's a positively charged atom that is less acidic than this neutrally charged compound. So there are some caveats. We're going to say that this is true within relative comparison. It's really hard to put into words. What I'll tell you is that when I want you to use this trend, you won't have to guess or find some weird instances like this. It will be very obvious that you're using the trend of charge to rank acidity. Let's look at an example. One of the best examples. It's similar to water, but we're going to apply it with our organic molecules. Here's CH3O- compared to CH3OH, which we had here and we had here. And the last one we'll look at is the CH3 OH2 plus. Which of these species is the most acidic? The one with the most positive charge. And which of these is the best base? This compound can accept electrons far better than these two. And this compound can donate hydrogens far better than these two. Best acid, which means most negative pKa. Lowest pKa. And here's our best base. Highest pKa. I gave you guys some rules with resonance, and I told you those resonance rules are priority based. CARIO is not priority based. It's just a good way to remember the components. So we're not going in order of first look at charge, then look at this, then look at that. It's just a good way of keeping them all organized. A stands for atom. And there's actually two things we need to compare. Within a row, a more electronegative atom is more acidic. So here's a good molecule that helps us compare acidities within a row. Carbon bonded to hydrogen, nitrogen bonded to hydrogen, and oxygen bonded to hydrogen. Carbon, nitrogen, and oxygen are all in the same row. So I can predict that acidity is ranked by its electronegativity. OH, best acid, lowest pKa. CH, worse acid. This has the highest pKa. And that agrees with our correlation table here. That CH bond has a pKa in the 50s or 60s, and OH was all the way up there around 15, and we see NH around 30. Within a row, comparing those atoms, more electronegative, more acidic. But what about within a family? Within a column, more polarizable. Polarizable is more acidic. Some of you went home and said you were going to look into polarizability. Did you? Do you have a better idea of what it means today? Let's look at this molecule. This molecule has both an OH group and an SH group. It also has CH groups, but we can see that CH groups are really not acidic. What's going to be a better acid here? The OH, will it donate its proton? Or the SH, will it donate its proton more readily? So Hayden's saying OH. Everybody else has glazed eyes. What is polarizability? Or what is it the result of?
It's like the the electron cloud shaping itself, right?
Yeah, it's the ability of the atom's electron cloud to create dipole moments on its own. So does a larger atom create dipole moments better on its own, or does a smaller atom? The larger atom has so much more space for its electrons to end up further away from the nucleus or vice versa. So the larger the atom, the more acidic the atom. Better acid. I don't think that I have SH on this periodic table or on this chart. Oh, I sure do. You can see it's not much more acidic compared to an OH. So polarizability has an effect, but it's not necessarily the same effect that electronegativity has within a row. Electronegativity took me from 15 for OH, 35 for NH, and 50 for CH. Electronegativity played a big role. Polarizability plays a smaller role. Let's look at another really common family, the halogens. HCl, HBr, HI. Iodine being the largest in the family is the most acidic. How many of you have ever worked with hydrofluoric acid? Yeah, of course. You've worked with it?
I'm part of a research study for the geology department and use it to study like microfossils.
Yeah.
And we have to like dissolve the organic matter around it.
I think it's not even the organics. The HF is really good at dissolving calcites or something, like some metal inorganic complexes. Have you been trained on the safety of HF?
It's okay.
A lot of research labs.
Like in the fume hood, and we have to like dress. We have to wear a lot of stuff.
A lot of research labs that work with HF regularly have signs posted on the doors that say, danger, death is imminent if you come in. HF is incredibly scary. It actually doesn't leave acid burns on your flesh in the same way that HCl, HBr, HI, or H2SO4 do. Instead, it seeps right through your flesh and it disintegrates your bones. It breaks apart all of the inorganic material in your bones. So it's not very acidic. It has the lowest, you can see HF here is a pKa of 3. HCl is a pKa of -7. But it is one of the scariest acids to work with because of its other properties, its ability to interact with inorganic complexes. Be careful. All right, let's move on, shall we? After atom, we're going to look at resonance. So what we can say is that increased resonance stabilizes a charge. A charge is the reason that something is either acidic or basic. So when there is increased resonance, that base is either a weaker base or that acid is a weaker acid. So I'll give you a couple of examples. If we look at this compound, acetic acid, and we introduce it to a proton, there are two things that can happen. The oxygen on the top accepts the proton and becomes positively charged, or the oxygen on the bottom accepts a proton and becomes positively charged. There are two places where the oxygen could be basic. But which of them is a better base? Well, the structure on top is actually in resonance, which delocalizes that positive charge. If the oxygen has taken a hydrogen, but now the positive charge is delocalized, it's not going to be a very good acid. Because by being an acid, you want to get rid of that H+, but now that H+ is delocalized, it's spread out. Whereas on the bottom, there is no resonance that can occur. There's no way that pi electrons can be moved in order to move that positive charge. So that makes this a weaker acid because the acid is stabilized by resonance. And of these two oxygens, this is the better base. It's a better base because it's a weaker acid. I want to give you another example. Here, I want to look at two different hydrogen bonds. Carbon-hydrogen bonds. And again, we're going to look at two different products that could form if a base is introduced. First, let's say that the carbon-hydrogen bond on the left is broken. That carbon takes on a negative charge. Then, we'll say the carbon-hydrogen bond on the right could be broken. That carbon takes on a negative charge. Should one of those carbons donate its hydrogen more readily than the other? Only if the conjugate base is stabilized for one of them more than the other. So if we look at this table, towards the very bottom, we've got CH bonds with a pKa around 50. But then up here towards the top, we've got a CH bond that is adjacent to a carbonyl with a pKa around 15. So why is this CH bond a better acid than this CH bond? It's because the second is in resonance. It's a better acid because its conjugate base is weaker. Once it does give away its hydrogen, it's less likely to accept a hydrogen back. So resonance is a really common way to predict what is more stable than the other, but you often have to look at the conjugate acid or at the conjugate base in order to know what will have resonance and what will not. Any questions so far?
Can you review that again? Because I'm a little confused about how the resonance on the top.
Yeah. Why does resonance make this oxygen a better base than this one?
Well, I guess I'm confused about comparing the two examples.
Well, one of them is identifying a better base by looking at the resonance in the conjugate acid. And the other is identifying a better acid by looking at the conjugate base, the resonance in the conjugate base. In order to determine a better acid, you often have to draw the conjugate base to see if there is resonance. And how do you identify resonance? It's that 3-atom charge with a pi bond. 1, 2, 3. Resonance. Here, no pi bonds, no resonance, no conjugation, no p orbitals.
So if it has resonance, it's more stable. So it's going to be weaker.
Yeah. But you're often analyzing resonance in the conjugate. And resonance makes the conjugate weaker, which makes the starting material stronger.
Okay.
You're hitting the nail on the head, and you're really identifying the choke point here, which is the stronger the acid, the weaker its conjugate base. And the weaker the acid, the stronger its conjugate base. So resonance is one of the hardest ones because you have to analyze the conjugate base and then flip it on its head to understand something about the acid. Or look at the conjugate acid and flip it on its head to analyze the conjugate base.
Is that to say that if there was a hydrogen available in the first scenario, it prefers to go to that oxygen? If that second scenario we're trying to give up a hydrogen, it prefers to give that one before the other?
Yeah, so up here, if a hydrogen becomes available, this oxygen will take it. Because when it does, the conjugate acid is more stabilized. And if a base is introduced here, this hydrogen goes away. Because when it does, the base is more stabilized. You can make the theory, or you can make the assertion that all of the hydrogens can be accepted or donated at any of the positions. But to a very, very small extent. Out of 600 million billion molecules, maybe one of these hydrogens gets stolen. But a million billion of these hydrogens get stolen. In the world of chemistry, like almost anything can happen, but it's more about what happens statistically more likely.
So if we had a question on this, it would be like showing us one of the structures on the left. Is the O, is O1 or O2 the better base?
Yeah.
And then we would draw its conjugate acid and see if it has a resonance structure.
Yes. Or you could be given this example and then say, which part of CARIO explains why this is a better base? Is it charge? Is it resonance? Is it atom? Etc.
If it were that question, would you show us the resonance?
Yeah.
structure? Oh, okay.
Yep. So if I give you an example of a acid and base, or multiple acids and bases, and then I can say which explains why this prefers this direction, why this is a weaker acid, why this is a weaker base. All right. I stands for induction. Induction is often a poorly understood concept by chemistry students, but I really think that it can be thought of as moral support. But moral support can work in two ways, depending on what you want to do. Moral support can push electron density towards a specific atom, which changes its acid or base characteristics. Moral support can also pull electron density away from a specific atom, which changes its acid or base characteristics. So I'm going to give you both examples. First, induction, where electron density is pushed towards acidic atom. So you'll notice that I've got the same atom that I'm comparing, and I've got the same charges that I'm comparing, and I've got the same amount of resonance that I'm comparing. So the only distinction here is induction, electron density being pushed towards an acidic atom. And sometimes you want to analyze both the acid and the base form. This first example has very little electron density being pushed towards that O-. So we can try to draw the induction with a dipole arrow. All of those carbons and hydrogens, their electrons are being pulled towards the O-. Down here, I have a ton of electron density from each of these CH3 groups that are connected to this carbon. Which means that this oxygen experiences a lot of electron density coming towards it. It has induction into the negative charge. That's going to make that negative charge a stronger negative charge. And if it's a stronger negative charge, it's going to be a better base. So this is a better base, which makes this compound a better acid. A weaker base. A base that doesn't have so much electron density barreling down towards its oxygen, telling it to do something with its excess electron density and go steal a hydrogen. 9 times out of 10, induction in is the result of excess carbon groups morally supporting with their electron density, telling that O negative, go do something with your life. With your negative charge. The other way that we see induction is electron density pulled. From the acidic atom. One of the most common examples here is comparing acetic acid, which is the active ingredient in vinegar, comparing acetic acid with trifluoroacetic acid. Being highly electronegative, all of those fluorine groups are pulling electron density away from that oxygen. I'm going to draw the conjugate bases that form as well. And I'm going to show the conjugate bases with their resonance hybrid. That's to remind us that, once again, in these structures, we've got the same amount of resonance that forms in both of them. Carly, can you go? Thank you. I'm realizing I might not have given you guys these single lines. Instead, I think I introduced you to these, dot and dashed lines. But it's saying that the negative charge is delocalized. But it's delocalized in both of them, so they have the same amount of resonance. But this structure on the bottom, again, it's kind of that idea of moral support. The fluorines are saying, I'll take some of that excess electron density. I'll hold on to that excess negative charge. You don't have to do with it what you might need to do with it here. This makes for a weaker base, which means that this is a stronger acid. So induction has two effects depending on what type it is. Induction can say, here's more electron density, go be a base. Or don't be an acid. And induction can say, I'll take your electron density, go be an acid. Or I'll take your electron density, don't worry about being a base. I'll hold on to that negative charge. I'm anthropomorphizing it quite a bit, but if you want to, think about it as magnets. Having these big, strong magnets pulls away the magnetic effect from over here, makes it worse at doing its job. Any guesses what the O stands for? not oxidation, orbitals. And here's the trend with orbitals. More S character is more acidic. Which is to say, sp orbitals are 50% S, sp2 are only a third S character, and sp3 are only a quarter S character. So sp is far more acidic than sp2, is more acidic than sp3. And this can be relevant in the context of oxygen and nitrogen, but it is almost always only applicable to our carbon hybridizations. So let's take this structure and let's identify that we have 3 types of CH bonds. I have an sp to s orbital, I have an sp2 to s orbital, and I have an sp3 to s orbital. Which of these hydrogens is the most acidic? When a base is introduced, which of these hydrogens gives away its proton the most? That sp hybridized carbon. That's our best acid. Whereas this sp3 has the most positive pKa. It's harder for that sp3 to take it on. I think you can actually rationalize this not just by analyzing S character, but electron repulsion. When this hydrogen leaves and the bonding electrons become a lone pair set of electrons, those lone pair electrons don't have a lot of other electron pairs around it to be repelled by. It's directly linear from the next clearly obvious electron pair. Whereas here, the sp3 atom, when those electrons go back to the carbon, it has this electron pair and the other 2 bonding electron pairs that it's constantly being repelled by. Which kind of goes back to induction. More electron pair nearby is going to cause higher reactivity. All right, how are you feeling? That was a lot, and I haven't given you guys a break, and I'm sorry, and not sorry. So, these are the 5 parts that help you analyze differences in acidity, and you'll notice they don't all go perfectly together. They cannot be used as a list of priority, and there are interesting ways that they have compounding effects or deterring effects. So take, for example, the fact that carbon is less electronegative than nitrogen, but when carbon is sp hybridized, it's more acidic than an sp3 hybridized nitrogen. It's terrible. So when I give you questions that require CARIO to explain the ideas, I'm going to keep it within bounds. I'm either going to use multiple effects that have a compounding effect on the compound. For instance, it has more resonance, plus it has more electronegative atoms, plus it has more charge. But I'm not going to try and trick you guys. It can already be challenging enough to apply the concepts of CARIO. So don't take these questions thinking that you're being tricked. Take them and try to see how those 5 components play into ranking them. You guys will notice on the practice midterm as well that there's often questions that say, look at these atoms rank them by their acidity. And you'll use CARIO to apply it. All right, I've got one last thing to get through to you guys, which is Lewis acids and bases. And boy, is this a lot easier than Brønsted-Lowry acids and bases. Lewis acids, which are electron pair acceptors, are actually often called electrophiles. And throughout the semester, when we look at electrophiles, I'll abbreviate it as E+. Not that every Lewis acid is positively charged, but it reminds you that an electrophile wants to accept electrons. These either have partial positives, or electron deficiencies. So I'll give you guys a few examples of our Lewis acids. CH3Br, CH3I, CH3Cl, any carbon group bonded to a halogen, often an electrophile, because of that partial positive on the carbon. And so we really say that the carbon is electrophilic. It wants electrons. It will accept electrons from something else. We can also have structures like this. That's a 4-carbon structure with a positive charge. I think we looked at it earlier in the week or last week. That's a true positive charge, as well as an electron deficiency. That carbon doesn't have a full octet. That carbon is electrophilic. And then one of the last ones that we look at in organic chemistry is a boron center. A boron doesn't have a partial positive. Oh, I guess that's not true. It is partial positive relative to the hydrogen, slightly. But it doesn't have a true positive charge. But boron is an odd atom in that it has an electron deficiency. It doesn't have an octet, and that's when it's neutral. It only has 6 electrons around it. That's when it's neutral, which means that it can readily accept electrons and fill its octet. Lewis bases. These are electron pair donors, and they're often referred to as nucleophiles. And I'll abbreviate that as nuc minus. Not all nucleophiles are negatively charged, but it reminds us that nucleophiles have electrons that they can share to something like an electrophile. So these often have a partial negative, a full negative, or pi electrons or lone pair electrons. I'll give you guys some common examples of nucleophiles, Lewis bases. CH3OH. And you might compare that to CH3Br and say, carbon and bromine have the same difference in electronegativity. They have the same electronegativity value. Carbon's not even partially positive based on a difference in electronegativity. And yet you still call it an electrophile because of that idea that it does accept electrons, and bromine takes electrons more easily. Whereas in CH3OH, carbon definitely has a positive charge, but instead, it's the lone pair and partial negative on oxygen that makes CH3OH and all other atoms like that nucleophilic. This is another compound we'll use later in the semester, where the carbon holds on to a lone pair, takes a negative charge. That's a nucleophile. Here's another fun one that I like. This is the azide structure, N3 minus. And N3 minus is a nucleophile. It's got that excess of electron density that it can use to attack. There's another one. It's pretty odd. It's not one that we'll look at a lot, early on, but it's one that will become really relevant later in the semester, and that's actually the pi bond between carbons, a carbon-carbon double bond. That carbon-carbon double bond can be nucleophilic. Now the reactions between Lewis acids and Lewis bases, this is where electron arrow pushings become really relevant, very prevalent. So here's a common one that textbooks will use to introduce Lewis acid-base reactions. They'll take a solvent like diethyl ether, and they'll mix it with borane, which we know is an electrophile. Diethyl ether is a nucleophile. Lewis base, Lewis acid. And the product that forms is referred to as an adduct. It just means that it forms a bond between them. And in this case, boron does take on a negative charge and oxygen takes on a positive charge. Now what we want to do with electron arrows is show how the electrons had to change in order to break or form the bonds that are shown. Let's spot the difference between starting material and product. What changes? Oxygen loses a lone pair, forms a bond to boron. So oxygen must use its lone pair to form a bond to boron. That's pretty simple. Let's look at one where something like methanol reacts with this methyl bromide structure. And you can see I've highlighted the CBr bond. I'm missing a couple of things in the product that I'm drawing. There's a negative charge on the bromine. That's a bromide ion. And there's a positive charge on the oxygen. And if it helps you to draw in all of these lone pairs, do not hesitate to do that. Can we spot the difference? What has changed from starting material to product? The CBr bond breaks. When a bond breaks, how are those electrons allowed to move? They move towards the more electronegative atom. John, carbon and bromine aren't more electronegative than each other. I know, that sucks. So think of bromine as being more electronegative. Those electrons are given to the bromine. That's how bromine got its fourth lone pair. It took the bonding electrons. What else changed? Oxygen had a lone pair, and it no longer has a lone pair. So how did it do that? Oxygen used its lone pair to bond to the carbon. In your unit test this weekend, you will have to do some questions revolving arrow pushing. You'll either be given starting material and product, and you'll be asked to show the arrows that perform the reaction as shown, or you'll be given a starting material with arrows, and you'll be asked to show the products that form. I've been using this idea of spot the difference, and I can't emphasize it enough. Make a list of all the bonds that break. Make a list of all the bonds that form. And recognize that when a bond breaks, the electrons go to the more electronegative atom. And when a bond forms, electrons have to come from an atom to the partial positive.
Real quick, is it always left to right when arrow pushing?
Not necessarily. We're going to do reactions this semester where we do a lot of arrow pushing, and I'll run out of space, and I'll have to kind of loop around. As long as so what should be done is that your arrows show the transformation that's needed to form the products on the reaction arrow. You never show arrows on the products that would show how the starting materials are formed. You always pay attention to which way the arrow is going. All right, I'm excited to see your unit tests this weekend. Or really, I'll see your unit tests next Tuesday afternoon. Remember, 2 attempts on part A, so space them out so that you can do some studying in between. 1 attempt on part B, you'll need to take a picture of your work, whether you do it on a laptop, an iPad, a whiteboard, a piece of paper, and you'll need to upload that to the unit test. If you have any troubles with that, you just send me an email. Good luck, guys. Have a great weekend.
How long are each parts? Like how many questions?